Hey guys, in this video we are going to talk about this problem in more details. So this is our initial value problem, right? So first order differential equation with the initial condition. So this is called initial value problem, right? So alright, so today in this video we are going to talk about well-posedness of this initial value problem. So actually there are three conditions that need to be satisfied in order for this uh, initial value problem to be well posed, right? So let's talk about that, right? Let's look at what are those initial conditions, right? All right, so first one, there exists a solution to this initial value problem, right? And that solution needs to be unique, right? That is the second one. And the third one is solution's behavior changes continuously with respect to the initial condition. So the final one is called the stability of the solution, right? So first one, there exists a solution to this initial value problem. The second one, the solution needs to be unique. So the third one, solution's behavior changes continuously with respect to the initial condition. Then we say this problem is well posed. So this problem is well posed, right? If these conditions are satisfied, then we say this system is well posed. If one of these does not satisfy, then we say this system is ill posed. Right? So if this problem satisfies all these conditions or there, so what are the conditions? There exists a solution to this system, and solution needs to be unique, and the solution's behavior changes continuously with respect to the initial condition. If these conditions satisfy, and then we call this problem is well posed. If one of these does not satisfy, then we say the system is ill posed. For instance, if you look at this system, this initial value problem, it is very difficult. It is very easy to get an exact solution to this. When you solve, you can separate variables, right? You can obtain exact solutions. So you will get y equals e to the 2x, something c times e to the 2x. So here, when you solve this differential equation, you get a family of solutions. And because of this initial condition, you can find this arbitrary constant, right? When you plug this value into the equation, you will get the value of c. So you get something like this, right? So this is a solution. So this is a solution to this, right? So we can say this system, there exists a solution to this system. So you can say, so this first condition satisfies, right? So for this initial value problem, there exists a solution to this. Yeah, there exists a solution. So in general, for an initial value problem, we can say there are there are there is a unique solution, or there are many solutions, or there are no solutions. So we can say, if you are given an initial value problem, you can say there is there is a unique solution, there are many solutions, or infinitely many solutions, or there are no solutions, right? So I don't have time to explain this concept by giving examples. Just say, if you are given any kind of initial value problem, there are three conditions. So three conditions. One is might have a unique solution, or infinitely many solutions, or there are no solutions. Okay, so we can prove that if this function f is a function of two variables, if this function is differentiable on a considered rectangle, so we can say that this system has solution, right? So I don't have time to prove those things, right? So I'm just saying, if f is differentiable in a certain rectangular domain, right? So we can say, we can show that this system has a solution, right? So if you want to check whether this has a unique solution or not, we can check the differentiability of f with respect to x here. So this is the dependent variable. So f is differentiable with respect to x, then we can say this has a unique solution. This system has a unique solution, right? So for that, I will explain this ellipsis continuity, right? So if uppercase f is a function of two variables, right? So D is a domain, a subset of R2 plane, right? So if this one is ellipsis continuous with respect to y variable, right, on D, if there exists a constant L such that, so this inequality satisfies, right? So f is said to be ellipsis continuous with respect to y on domain G. So there exists a constant. Such that, so the modulus of these two, right? Modulus of f of x comma y minus f of x comma y star less than or equal to that constant L times modulus of y minus y star, right? This is true for all x comma y and x comma y star in this domain, right? So this L is said to be ellipsis continuous, right? This ellipsis constant, all right? So this one is very important, and these x coordinates that do not change here. Don't change this x coordinate, and we have to consider y and another y star. So in the domain D, right? So these are 2 points in the domain D, right? So let's do this example. Show that this function is a function of two variables x and y. Function is defined this way, and we have to show this function is ellipsis continuous in this domain, right? Okay, let's show that. So the domain is defined as consider rectangular coordinates x comma y. So x is bounded by 0 and 3, and y is not bounded, right? All right, so find the ellipsis constant L. So let's do this one. All right, let's do this one here. Let's take any 2 points in this domain, right? This is your domain, so these two, we picked any 2 points in the domain D, right? And we consider this one left hand side, the modulus of f of x comma y minus f of x comma y star, right? Okay, so the modulus of 3x squared y minus 3x squared y star. So here x does not change here, right? So you can take out 3x squared because it is common. This is a common factor, right? You can take it out from the modulus sign because this is a non-negative number. 3 is positive, this is a non-negative number. So modulus of this gives you itself, right? So 3x squared times modulus of y minus y star. So you know that y is bounded by 3 and 0 and 3. So the maximum value, so you can find the, so here this is the bound, these are the bound. So you know x squared is increasing on this interval, right? Increasing. So you know that x squared is less than or equal 3 squared on this interval, right? On this interval, this one is true, this inequality is true. So you can replace 3 squared with x squared, right? So then you get less than or equal 3 to the power 3 times modulus of y minus y star. So we showed that modulus of f of x comma y minus f of x comma y star less than or equal to this constant time y minus y star. So this one is the ellipsis constant. So big L is ellipsis continuous 3 to the 3, right? So this function is ellipsis continuous in this domain, and the ellipsis constant is 27, right? So let's go back to our problem. Yep. So there's that. Yeah. No. All right. This is your initial value problem. This is your function of two variables t and x. T is the independent variable, x is the dependent variable. X depends on t. So if this function is ellipsis continuous with respect to dependent variable, here dependent variable is x. If this function is ellipsis continuous with respect to x, then we say this system has a unique solution. So I saw a lot of questions were given in past papers about ellipsis continuous If you are given a system like this, so if you want to check whether this system has a unique solution, you can check. You have to show this function is ellipsis continuous with respect to the dependent variable x. Here the dependent variable, don't get confused, the dependent variable here is x, not t. T is the independent variable, here x is the dependent variable, right? So this one is very important when you deal with initial value problems. If you want to check this system has a unique solution, all you need to do is check whether f is ellipsis continuous with respect to the independent variable x, right? So here look at this theorem. D is an open set. F is a function of d. So d, yep, f is a function continuous given that. Then there exists at least an integral curve through this. Furthermore, if this one is continuous in that domain D, then we can say, or differentiable, that is very strong. If this function is continuous in that domain D, then we say this has a solution, right? There exists a solution to this system. However, and I want to mention this one here. If furthermore this is up to boundary D, f is ellipsis continuous with respect to y, then the solution is unique. So look at this. Show that this initial value problem has a unique solution. All you need to do is show this function is ellipsis continuous with respect to the dependent variable y. A dependent variable is y. X is the independent variable, right? So show that this function is ellipsis continuous with respect to y. Then you can say this system has a unique solution, right? So I hope you understood existence and uniqueness. If this one is differentiable, continuous on the domain, right, D, then this system has a solution. There exists a solution to this system. If f is ellipsis continuous with respect to the dependent variable in that domain D, then we can say that solution is unique. The solution to this system is unique if f is ellipsis continuous with respect to the dependent variable x here, right, in that domain. Alright, I hope you understood this ellipsis continuity, right?